The pair of capacitors in the figure below are fully charged by a 6-volt battery. The battery is disconnected and the switch is then closed. A. After 2 milliseconds has elapsed, how much charge remains on the 3 microfarad capacitor? B. After 2 microseconds have elapsed, how much charge remains on the 2 microfarad capacitor? And C. What is the current at the resistor at this time? Alright, so since part A and B ask a very similar problem, we're going to solve both of those at the same time. So first, it tells us that the whole circuit was charged with the voltage equal to 6 volts, and it asks us to determine the amount of charge left on the 2 capacitors after 2 milliseconds. So first, we got to determine the original charge. And to do this, we got to use our fancy equation here. Q is equal to capacitance times EMF, which is basically just voltage. And for this capacitor up here, Q, I'll label it 3 because it has a capacitance of 3 microfarads, is equal to the capacitance times the EMF, which is 6 volts. So we know the original charge on this capacitor right here is equal to 18 microcoulombs. That's very nice. What if we try it for the second capacitor? Again, using the same equation, we go Q sub 2 is equal to the capacitance, 2 microfarads, times the same EMF, so 6 volts. This means that the original charge on capacitor 2 is equal to 12 microcoulombs. So now we have the original charge. We got to write an equation for the charge over time. And in an RC circuit, we know that Q of T is equal to original Q, denoted by a capital letter Q, times E to negative T over RC. Then we got Q, we got the R, and we got the C. I think this could be done. Starting off the first capacitor up here, we'll go Q sub 3 of T is equal to that original charge, 18 microcoulombs, times E to negative T over, well, we know what the resistance is, it's just 500 ohms. But what do we multiply it by? Do we do the whole capacitance of the circuit, or just the capacitance of the one capacitor? This is where I got a little tripped up myself, but in reality what we have to do is multiply it by the total capacitance of the circuit, because this equation models the behavior of the circuit as a whole, not just the individual capacitor. So since we got to multiply by the total capacitance, we got to multiply by 5 microfarads. So that's our equation for the charge at that capacitor over time. So to solve for 2 milliseconds, which is 0.002 seconds, we take 0.002 seconds, put it into T, solve, we get a value of 8.1 microcoulombs. So after 2 milliseconds, the charge on this capacitor goes from 18 microcoulombs to 8.1 microcoulombs. In a similar way, using the same equation here, you could solve Q2 of T, which is the charge on this capacitor over time. This is equal to the original charge there, 12 microcoulombs. Again, negative T over RC, the C is the total capacitance in the circuit. Five microfarads. Again, it's asking for the same time, so we put in 0.002 seconds. And this yields a value of 5.4 microcoulombs. So this is your answer to part A. Part B. And then part C asks us to find the current going through the resistor at this time. I think we could do some calculus here. We'll bring it on over here. So we know that current is the time derivative of charge, right? Okay. And using our basic general equation for charge, it means that current is the time derivative of Q times e to the negative t over RC. When you take the derivative of this expression, Q is a constant, so you can just take that out. And whenever you take the derivative of e to the any power, it's always a derivative of the power times the whole thing. So what's the derivative of negative t over RC? Just negative 1 over RC times e, again, the negative t over RC. Basic calculus. Q, we determined over here, was the capacitance times the EMF. This means that the capacitance here is cancel out. So what we would get is negative the EMF over the resistance times E, the negative T over RC. And asking for the same time, so at 0.002 seconds. EMF 6 volts, resistance 500 ohms. Time 0.002 seconds. And again, RC, it's the resistance times the total capacitance in the circuit. So this will be 500 ohms times 5 microfarads. This yields a value of 5.4 milliamps. Very nice. When I was first doing this problem, when I was substituting for RC, I was messing up and putting just the capacitance of the one capacitor, because that's what I did to determine the charge. But this right here is actually a time constant, which we go by thou. And this time constant is not unique to each capacitor. It's a quality of the whole circuit. So we had to do the total resistance of the circuit times the total capacitance to get this time constant. Even though we used this time constant in determining the charge on this capacitor, and the current through this resistor. It's not unique to one element of the circuit. It's unique to the circuit itself, and everything in the circuit has the same time constant. And this problem shows my growth because it shows that I understand more complex circuits that aren't just a battery and a resistor. It's capacitors and resistors, and I'm able to take derivatives of charge to solve for current. I'm able to solve for the charge in a capacitor in an RC circuit as an expression relating to time. Thanks.